Okay, so we're working out in the previous lecture. We'll continue with stability boundaries. And remember, the idea here is that for the Mathieu equation, d2y dt squared equals, plus a plus 2 epsilon cosine t, y equals 0. We won't specify any initial conditions here. We expect periodic solutions. And it could be stable or unstable. But the main way we determine whether they're stable or unstable is that we perform some sort of perturbation expansion. We take some multiple scales for our time variable, and what we expect to find is that we have some oscillatory solution to first order with a slowly varying modulation of the amplitude, okay? And what we need is for A of tau not to grow. In general, we expect that A will be either of the form IB or B, either some imaginary part which would make this like a sine function, or B that would make this more like a cosine function. And then we expect that B of tau is going to be some constant times an exponential plus or minus some Foucault multiplier mu times tau, okay? And in particular, we need that the real part of mu needs to equal 0 for stability. If the real part of mu is either positive or negative, due to the reflection symmetry of the problem, we should expect to find that the amplitude is going to grow over time, okay? So in general, we want this to be pure imaginary or 0, for instance, so we just have a constant coefficient. And so far, right, we found that A equals 1/4 plus epsilon plus A2 epsilon squared plus some order epsilon cubed terms are going to be the stability boundary near A equals 1/4. So we sort of drew this out here for A and epsilon. And so we can draw this here, and we say that we should expect to find stable solutions just the other side to the right of this, and unstable solutions to the left of this. Okay, so for A greater than this sort of A critical, and A less than this sort of A critical boundary here. Okay, so we worked out A1 equals plus or minus 1, okay, using the epsilon hierarchy for tau equals epsilon t. Okay, and we're working out A2 using an epsilon to the 1/2 hierarchy for tau equals epsilon to the 3/2 t. On your homework, you're going to use tau equals epsilon squared t to recover A3. Okay, so we had worked through essentially the first several equations in the hierarchy. Okay, and to this point last time, we'd found that for t, sigma equals epsilon to the 3/2 t, and then y is an expansion in epsilon to the 1/2. What we found is that dB dt so for y0 equals A0 tau, A0 of sigma, e to the I t over 2 plus a bar 0 sigma e to the I t over 2. We had found that A0 should be of the form I b0, where this is some real function. We'd also found that minus dB d sigma is equal to A1 of sigma minus A1 bar of sigma, where Y1 is equal to A1 of sigma e to the I t over 2 plus its complex conjugate. Okay. We found that by eliminating secular terms at order epsilon to the 3/2. And then at order epsilon squared, what we'd found was that minus I A1 plus A1 bar, let's write this as a derivative using differentials, sigma with a minus I out in front, is equal to IB plus 2A2IB. Okay, so if we set C equal to A1 plus A1 bar real, right, because we should get cancellations, we sum up the conjugates, then we end up with dB d tau is equal to, dB d sigma is equal to C of sigma. And we get that dC d sigma is equal to minus 1 plus 2A2 B of sigma. Okay, this is just a linear second order differential equation with off diagonal entries. And so we get that d2b d sigma is equal to minus 2A2 plus 1 B of sigma. We can easily solve this to get that B of sigma is equal to beta exponential of plus or minus I square root of 2a2 plus 1 times sigma. Okay. And so what we find is that in order to keep the multiplier up here pure imaginary, we need the argument of the square root to stay positive. Okay. So we're going to get stability when A2 is greater than minus a half. Okay. And we'll get instability when A2 is less than minus a half, because then the square root of this would give us something imaginary. We'd end up with an exponential, okay, that has a real multiplier, and we'll get growth for the case of the minus one there. Okay. So now we finally have our critical stability boundary, A of epsilon up to second order, 1/4 plus epsilon minus epsilon squared over 2 plus order epsilon cubed, okay, as epsilon goes to 0, okay. So we can draw this now. It'll look something like this. You can look in Bender and Orazag for a full diagram, right? I think this is the last section of the book. And what you should find is that right around a quarter here, we have the stability boundary that goes out, and then it sort of bends back because of this quadratic part here. And on this side, we have unstable. And on this side, we have stable solutions, okay? And we can do this around all of these special points of secularity here. We can perform these perturbation expansions around them. And there's a general way to extend it to arbitrary n in this case, okay? But basically in the homework, you'll extend to A3 in the homework, okay? Now, why is this useful? Okay, why can't we just get this from numerical simulations? Well, that would be, much more computationally expensive. Also, you have to run things for a long time in order to see whether you have a breakdown in stability. Okay, this gives you a qualitative picture across a wide range of parameters. Okay, so by just spending, a couple hours working through the stability boundaries here, we can develop a complete picture of essentially what happens as we range across the A epsilon parameter space, okay? And this can be applied to a lot of periodic coefficient oscillator type problems. And as you can see, sort of building up the analysis is similar to other amplitude equation approaches that we've used. The main difference is that now we have these Flaquet multipliers. And in this case, we need them to just be pure imaginary in order to not generate instabilities in the amplitude. Okay. So you can try that out on the homework by extending to next order, where you have to use a time scale of epsilon squared t. Okay. So on to PDEs. Okay, I'm assuming, of course, that you have the prerequisite experience with wave equations in this case. If not, go back and review wave equations. We're going to lean on D'Alembert solutions a bit for this part. Okay. So resonance and issues of energy not dissipating, right? And that's really where all this sort of secularity canceling comes up, is because we have non-physical resonance appearing in the problem just due to the nature of the hierarchy of our perturbation expansions, and we're trying to remove that, okay? So resonance and issues of energy not dissipating, these can corrupt regular perturbations for waves, right? If you think of a string, it behaves like a spatially extended oscillator, right? If you force it at one end, you get spatial oscillations that will propagate along the string. And you can imagine that if you're forcing a string at the resonant frequency, energy can build up within it. And this can be problematic if you have perturbation expansions that generate resonance terms that aren't in the actual physical problem. Okay, so for instance, let's consider the example of a wave equation with a weak damping term here in the time derivative that lives on the real line. Okay, we'll take a simple case of this here, and then on your homework, you'll just have to extend it to a slightly more general case. All right, so in the homework, you're going to study in homogeneous initial velocity. Okay. All right. Now, this is a fairly standard initial value problem. Okay, just from PD, probably even if you took undergraduate PDEs, you would have seen this, except for this damping term here, right? So we're going to try first a regular perturbation expansion in order to account for this damping term. Okay. And we're going to see, of course, as you might suspect, that this is going to create a problem. So if I try a regular expansion here, right, let's just say, well, U can be expanded like so, right? I'm gonna plug it in. I'm gonna solve equations up the epsilon hierarchy. Okay, what happens? Well, at order 1, what we find is dx squared u0 dt squared u0 u0 x0 is equal to f of x, okay, and dt u0 x0 is equal to 0, okay. I'm going to notice that this problem, of course, has characteristics, so I can perform a change of variables. Theta minus equals x minus t, and theta plus equals x plus t. Okay. So then d theta plus d theta minus of u0 in this case is equal to 0. Okay, if I work through the change of variables there. So this means that u0 of xt is equal to f0 of theta plus g0 of theta minus, right? I get a constant, and then I can integrate it up. So if I plug this in, right, a differentiator works out. You can also, plug this in with the change of variables into your original equation and see that it works out, right? This is just the general solution to the standard homogeneous wave equation. And in particular, if we satisfy initial conditions, what we find is that we get a half f of x plus t plus f of x minus t. Okay. And just look back in your PDE textbook if you need a reminder of D'Alembert's formula. So that's all old hat as far as just linear PDEs go. But now let's say we have dx squared minus dt squared u1 is equal to dt u0 at order epsilon. Then we have 4 d theta prime d theta minus u1 is equal to minus a half f prime of theta minus f prime of theta plus, right? Just plugged in u0 here. Use the definition of my characteristics. And so what do I get? I get that if I solve this, u1 of xt is equal to minus theta plus f of theta minus divided by 8 plus theta minus f of theta plus divided by 8, right? Integrating once just removes the differentiation. Integrating twice gives me these theta plus and theta minus terms out in front of each of these variables. Okay. And then just like in the case of the order 1 equation, I have these homogeneous solutions, f1 of theta plus and g1 of theta minus. Okay. So this is a secular term. And this is 1, 2, right? Why? Well, because as these characteristics get large, this is going to build up. And I'm going to have larger and larger oscillations in the string, even though there's not really any resonant forcing that should cause that. Okay. And there's no way to prevent them. So what do we do? Well, we probably should apply some sort of multiple scales approach. Now, the issue is here we have time and we have space, and it's not always clear necessarily which of these to choose in order to introduce multiple scaling. Okay. So we're actually going to list possible multiple scalings. For instance, one of these could be T1 equals T, T2 equals epsilon T, X1 equals X, X2 equals epsilon X. Another of these could operate off of the characteristics though. Theta plus equals X plus T, theta minus equals X minus T, phi plus equals epsilon theta plus, and phi minus is equal to epsilon theta minus. Okay. And lastly, we might want something that to order 1 sort of respects the characteristic structure of solutions. Remember, at order 1, we can write our solutions out just in terms of our characteristics. Okay. But once we get beyond order 1, right, we're going to start breaking up this nice structure, right, of our original wave equation. So maybe we don't expect that we should write out the solution just in terms of characteristics or just rescalings of them. So we need a mixture of characteristics and these rescaled variables. So the other possibility is then to have this mixed scaling here with characteristics at order 1, and then our stretched stretched coordinates are going to be just in T and X. Okay. So we're going to try this first. Okay. And it turns out that it works. You could try the other scalings, right? But the logic essentially is that I'm breaking up the ability to just write things in terms of characteristics once I go to higher order. Okay, it's no longer just a standard wave equation. So in this case, dx is going to get mapped to d theta plus d theta minus plus epsilon dx2. And dt is going to get mapped to d theta plus minus d theta minus plus epsilon dt2. Okay. So if we sub this into our PDE, let's remind ourselves just what that PDE is here. Right, it's this thing. Okay. What we get is 4 d theta plus d theta minus. Okay, that's what we get from dx squared minus dt squared. Now for the order epsilon terms, though, we get 2 epsilon d theta plus d theta minus dx2 minus d theta plus minus d theta minus dt2 plus order epsilon squared terms. Okay, and we're only going to go up to order epsilon is equal to epsilon d theta plus minus d theta minus plus order epsilon terms u. Okay, so along with this, we need to remember our initial conditions, okay, which now are for any x, right? And for any x, right? And as long as t equals 0. Well, whenever t equals 0 in these characteristics, right, we are going to have that theta plus and theta minus is equal to x. And then for our other coordinate t0, t is going to be 0, so t2 is going to be 0 in this case. Okay, so this is basically the t equals 0 condition. We have that u of theta plus theta minus, that would be theta minus in this case, x2 and 0 is going to be equal to f of theta minus, okay, and d theta plus minus d theta minus plus epsilon dt2 acting on u theta minus x2 0 is equal to 0. Okay. All right. So if we expand this solution now, what we have is u is approximated by u0, theta plus, theta minus, x2, t2, plus epsilon u1, theta plus, theta minus, x2, t2, plus so on and so on. Okay. So our order 1 term is going to be, or order 1 equation is going to be 4 d theta plus d theta minus of u0 is equal to 0. u0 is equal to f of theta minus, and d theta plus minus d theta minus of u0 is equal to 0. This occurs for theta plus equals theta minus, and for t2 equals 0. Okay, so this implies then that u0 is equal to some function a of theta plus theta minus t2 plus b of theta plus theta minus t2. Okay, and notice that there's no x2 here. Essentially, since the initial condition does not depend on x2, okay, we will assume u0 does not either. Okay, we don't have to inherit dependence on that variable. Okay, and so we can exclude it in order to have fewer variables to deal with. If it turns out we need it to remove secularity, a problem will arise at that point. Okay, so that means that u0 of theta plus theta minus t2 is equal to F0 of theta plus T2 plus G0 theta minus T2. Okay. So all that happens now, if we compare with the previous case, right, is that we've added dependence on T2 to these different parts of the solution. Okay. All right. At order epsilon now, we have 4 theta plus d theta minus d1, and now the terms come in. That provide the forcing that we're going to have to cancel in order to remove secularity. Okay. If we substitute in U0 and solve, what we get is that U1 is going to be equal to theta minus divided by 4 times 2d T2 plus 1 F0 minus theta plus over 4 2 dt2 plus 1 G0. Okay, so it looks somewhat similar to last time, but now because of this additional derivative term by the slow variable, that enters into the secular terms. Okay, and in addition, we have F1 of theta plus T2 plus G1 of theta minus T2. And we don't care so much about these terms, we just care about removing the secular terms. And you can see already now that we have a differential equation for what F0 and G0 should be. Okay, so to prevent the secular terms, we just have to take 2 dt2 plus 1 F0 equals 0, 2 dt2 plus 1 G0 is equal to 0. Okay. And we end up then with F0 is equal to F of theta plus over 2 e to the minus T2 over 2. And G0 is equal to F of theta minus over 2 e to the minus T2 over 2, basically using the initial conditions that say that U of 0 should equal F of theta minus for theta plus equals theta minus, and also that d theta plus minus d theta minus U0 is equal to 0. Okay, where theta plus equals theta minus and T2 is equal to 0. Okay, this gives us our initial condition that gives us our constant out front, except it's not a constant, it's a function of the characteristics here. So therefore, what do we have? We have that U is approximated by a half F of x plus t plus F of x minus t e to the minus epsilon t over 2. Okay. So interestingly, this is actually highly accurate. In fact, it's exact. Okay. And that's because we don't have any velocity term that would involve an integral, right? So everything here is pretty much linear. And you could actually use an ansatz to derive this, right? Exact solution. Okay, so this will not happen for non-trivial initial velocity. See homework for that case. All right. So what was the idea there? Okay. We included multiple scales, but now we include multiple scales in both time and space because this is a PDE. And at lower order, we just use the characteristics because that's what solves a standard homogeneous wave equation for us. Okay. When we expanded the solution, we found that we did not need even the spatial variable, and it was sufficient just to include the slow time variable. Okay. And then these initial conditions are going to help us specify the solutions F0 and G0 here, which are going to involve the functions of the characteristics out in front. Okay. So similar looking to D'Alembert's solution, except that now we have this slow exponential decay due to the damping term that's been included. Okay. All right. So in the time that I have left, I'd like to introduce concepts in nonlinear waves. So let's talk about nonlinear waves. Okay, we talked about these briefly at the end of PDE. Okay. And we can extend, right, our multiple scales approach to nonlinear PDE. Okay. And we're going to focus on one example in this case. It's going to start off looking a lot like the linear wave equation, but we will introduce a cubic term. And we'll call this equation star. It has some initial condition. Okay. And in particular, it's called the Klein-Gordon equation. It's relevant to models of plasma waves, okay, and strings on elastic foundations, okay? And it's this nonlinearity that leads to some interesting behavior. Now, if we take epsilon equals 0, note that by Fourier transform, okay, we can get solutions of the form U, A of k e to the I kx minus omega t dk plus minus infinity to infinity integral e to the I kx plus omega t dk. Okay. And omega equals square root of 1 plus k squared. And A and B are going to be determined by our initial conditions. Right? Okay. So one way to see that, right, is if we write this out, we have minus k squared u hat kt is equal to dt squared u hat kt plus u hat kt. And we can rewrite that as d2 dt squared u hat kt is equal to minus 1 plus k squared u hat kt u hat of kt is equal to some A plus or minus e to the minus or plus omega of k t, right, which appears up here, where omega of k is equal to square root of 1 plus kappa squared, okay? And then essentially we invert the Fourier transform to return, okay? And you're going to have some, 1 over 2 pi showing up there too, okay? Now, that's the linear equation, but of course we're interested in how the nonlinearity changes things, okay? So sort of guided by this, we can study how nonlinearity alters these plane wave type solutions, okay? U plus or minus is equal to e to the I kx plus or minus omega t, okay? So let's just expand about the right moving wave, sort of make an ansatz that we have u of some form u0 of kx minus omega t. So we set the initial conditions so that we get a solution like this, plus epsilon u1 xt. Okay. Now, if we did this, it would yield secular terms, okay? And you can see that in the typical way that we see it. I won't go through it, right? So we need multiple scales, right? And so if we take theta equals kx minus omega t to be like our characteristic, y equals epsilon x, and tau equals epsilon t, then we have some multiple scales to work with that'll help us remove these secular terms, okay? So if we assume, right, that our omega is equal to some square root of 1 plus some frequency squared for k greater than 0, then we have dx is mapped to k d theta plus epsilon dy, and dt is mapped to minus omega d theta plus epsilon d tau, okay? So this means that our PDE becomes d theta squared minus 2 epsilon k dy plus omega d tau d theta plus some order epsilon squared terms acting on u plus u plus epsilon u cubed equals 0. We're going to expand now u as u0 theta y tau, right, in our slow variables in addition to the characteristic variable, okay? And then isolate powers of epsilon in this case, okay? So as I do this, what I should find is that at order 1, I get d theta squared plus 1 u0 equals 0. The typical thing happens, right? I get u0 is equal to some amplitude of my slow variables times, and I'm going to write it out in terms of cosine with a shift now, cosine of theta phi y of tau, okay? So now I have A and I have phi, which I don't know. And those will be involved in future amplitude and phase shift equations. Now, the heterogeneity comes in at order epsilon, Okay. I have a cubic term, and now I have these derivative terms that have come from introducing multiple scales. I can write this out now. It's a bit lengthy, as 2 times k dy plus omega d tau a sine of theta plus phi minus a cubed over 4 cosine of 3 theta plus phi, using some trig identities, minus 2 k dy plus omega d tau phi plus 3a squared over 8 a cosine theta plus phi. Okay, so I had to do some differentiation, expanding this out, grouping terms together, applying some trig identities, some steps in between. Okay, but the point is, you can get this right-hand side, and clearly there's some secular terms, right? So what are the secular terms going to be in this case? Well, in particular, they're going to be the terms of the form sine here, okay? And this cosine term here, right? Because I'm going to have a theta plus phi, which is the solution to my lower order equation. Okay, so this is going to have the same frequency as my lower order equation's homogeneous solution, right? Which is the same operator that's occurring here. Okay, so I'm going to require, maybe I'll write them on the same line here so it's clear. K dy plus omega d tau a equals 0, and k dy plus omega d tau phi plus 3a squared over 8 is equal to 0. Okay, so this coefficient here and this coefficient here. Okay, now we can solve this, right? We can use characteristic equations. This is just really just a transport equation, right? This is like a transport operator plus just some inhomogeneity that you can solve for over here. So I'll take r equal to omega y plus k tau, and s is equal to omega y minus k tau. So then just dr of a equals 0, and dr of phi equals minus 3 over 16 omega k, right? Because we're going to get these extra terms popping up when I apply this characteristic here. Okay, so this means that a is equal to a of s, right? It's constant in r, and phi is equal to minus 3 over 16 omega k a squared r plus some phi of s. So I got my a and my phi, okay, and I can write u is approximated as a of omega y minus kappa tau, that's my s, cosine of theta, now minus my phi, which is 3 over 16 omega k, omega y plus kappa tau, that's my r that appears there, a squared acting on omega y minus kappa tau, plus phi 0 of omega y minus kappa tau. close parenthesis. Okay. So let's just say we take the following ICs. U of x0 is equal to alpha cosine kx, and u sub t x0 is equal to alpha omega sine of kx, and that this implies that u0 of theta y0 is equal to alpha cosine theta, and d theta of u0 theta y0 is equal to minus alpha sine theta. Okay, so this implies that if we plug this in, that a omega of y equals alpha, and that theta 0 omega y is equal to 3 over 16 kappa a squared y. So we can write u in a much simpler form now. Alpha cosine kx minus lambda omega t, okay, where lambda is equal to 1 plus 3 epsilon alpha squared over 8 omega squared, okay? And so this looks very much like your sort of standard transporting equation solution here, except that you have a velocity that depends linearly on the frequency to first order, but then nonlinear on frequency to higher order. Okay, so your phase velocity then, VPH, is equal to 1 plus 3 epsilon alpha squared over 8 omega squared times omega over k, right? So if we were to factor this out, right, factor out a k here, then we would have basically an x minus vt term. So for u is equal to alpha times cosine k times x minus vph t here, right? So that means that larger amplitudes alpha are going to lead to faster waves, which is not something that happens in linear wave equations. Okay, it's a non-linear property of these waves. Okay, another way that we could handle this is we could also assume u is equal to like f of kx minus omega t, and this would be like a traveling wave ansatz. Okay, and this is what you'll do in the homework problem. Okay, so that's enough for today. I know I've gone a little bit over, but it will mean there's a bit less to do on Wednesday of next week. So at this point, actually, you should have enough to do the first 3 problems of the homework. On Monday, you'll get enough background to do the last problem on the next homework. And then I think we might even be able to just wrap up nonlinear waves on Wednesday. So there won't be much for next Friday. Okay, see you all on Friday.